Hey, welcome back. In this video, it's kind of like a break video before we start getting into some bigger topics. I just wanted to cover two things, uh, differentiability and how to notate derivatives, or how to just write them out, or say that we're talking about derivatives. So first thing, what does it mean to be differentiable? Remember when I was talking about how you would have a graph, and when you were learning about limits, it was probably like, oh, there's an asymptote right here, and your teacher wants you to find the derivative or the limit as it approaches that value of x. Well, it's not defined at that value, right? So, uh, what a derivative is, like when I said we were talking about derivatives, how it's going to a specific defined point. Well, this is what it means to be differentiable. When you have a derivative, you can only find a derivative at a point that is defined. That's not the only criteria, but that is an important one. So, let's say I have a function, it's a cubic function, and it looks like this, but there's a hole at this x value. So if I was trying to find a derivative, I would have a function, and it would just kind of like look like this, and it would be normal like we talked about in the other videos. But if you got to this point where there's a hole and you wanted to take a derivative, you can't, because it is not defined at that point. And if you don't have a definition of like even a value, you can't take a derivative because it has no slope, because it's undefined. It doesn't get much harder than that. Now, what is the second criteria of being differentiable, or having the ability to take a derivative? I'm just going to write that down. Differentiable just means you can take a derivative. You can take, make, calculate. If it's undefined, there's no derivative. It's just that. The other criteria for being a derivative is when it's not like an abrupt switch. So say for example you have a piecewise function where it is y equals x, let's see, I don't know, 3x plus 4, and then that's until x is 5, like when x is less than 5, less than or equal to 5. And then 19, at x equals 19, it's just 19 for x is greater than 5. So on a graph, this would look pretty simple. It's just going up here. You have boom, x equals 4 until you get to x equals 5, and then it just flattens out with a slope of 0. Now, both of these functions, where y equals 19 and y equals 3x plus 4, you can take a derivative of both of these. The derivative of 19 is 0, and the derivative of 3x plus 4 is just 3. However, what about this point where it's a change? This is a defined point. 3x plus 4, where x is less than or equal to 5. Well, at x equals 5, the value is 19. Pretty simple. But because it switches and changes between them, that at that point there's no change. It's an abrupt switch, and it's not consistent. So there is no rate of change anymore. So you can't actually take a derivative at that point. It's not much more than that. If you learned about continuity while you were learning about limits, if it's not continuous, then you can't take a derivative at that point. Now, I can take a derivative from of here to here, and I can take a derivative from here to here, but I can't take it at that specific point. I hope that makes sense. That's what it means to be differentiable. And of course, if I have a function where it's piecewise and it looks something like this, and then, whoa, and there's this huge gap right there, of course I can't take a derivative in this part because it's a huge empty space. But I can take a derivative of all the other parts. So that's what that is. What it means is differentiable. This means you can take a derivative at that point. It has to be continuous. Now, second topic, how to write a derivative. So I've already gone over the fact that a derivative is nothing more than an equation or a number. But from here on out, we're going to be talking about derivatives as the equations. And the evaluation of the derivative is just going to be the specific values that you can get from it. So how do you write or say that something is a derivative? Well, for example, let's say I have f of x equals, I don't know, 3x plus 4. We use the same one. Now, let's say we solved the derivative and that was whatever I wrote here. And spoiler, it's 3, but that honestly doesn't matter for what I'm about to talk about. How do you say that this is the derivative? By essentially using this and then changing it. Well, there's a few different ways to do it. You can say f prime of x. Hope you can see that on the board. I wrote an f and then I gave it a little apostrophe, a cute little apostrophe right there. Yep, you can see it. So this means prime, and it's just saying, oh yeah, this is the derivative of the actual function. And you can go further, like you can take second derivatives, like inception, and then it would be f prime prime, I guess, of x equals 0. But the idea here is that you just have every derivative you take of the original, you just keep adding apostrophes, and that's it. And you can say like f prime x, and that's just saying I took the derivative of x. That's the first notation. Just going to write it up here on a little list. The other way to write it, f prime of x, is, say you have like y equals 3x plus 4. Now the way to write it is you can just take this variable, the dependent variable, and you write dy, or derivative y, over derivative x equals, well, spoiler, it's 3. That's the derivative. Now, this is not a fraction. That needs to be very clear in your head. This is not a fraction. Dy over dx, not a fraction. It's just a fancy way for mathematicians to be like, oh guys, look, it's derivative. Like, not a fraction. It is not derivative y divided by derivative x, not a fraction. It's just saying derivative. And what we've taken a derivative of is just this variable right here. So if I wanted to go back in time, it would be derivative y, or just y equals dependent variable x. So it'd be like whatever I have over here, which has an x in it. So this kind of works because it's saying our dependent variable is the derivative, and this is the variable that it is depending on the bottom. And yeah, and you can get creative with this as well. Like sometimes people will just write dx. I just write big D sometimes when I'm talking about it, like d equals 3, just for simplicity's sake. But you have to know that the top one is going to be the dependent variable, the one that is the function, the one you're taking derivative of, and the bottom one is the independent variable. Another way to spin this is say that you have an implicit function, or a parametric, sorry, where you have like y equals 3t, and then x equals 8t squared. This is something different. You'd have to go back to algebra to really learn about this, but essentially saying that like y is a dependent variable and x is a dependent variable, and they're both dependent on t, which usually stands for time. And you can get really creative with graphs of this, but the way you would write these derivatives would be dy over dt and dx over dt. Why? Because the first one is the derivative of y, so it's dependent on t, which is our independent variable, and d of x, and that's because x is our dependent variable, and 8t squared, it's t, so t. And this would be equal to 16t, and this would be equal to 3. Derivative of y is going to be 3, derivative of x is going to be 16t. Anyways, that's how you notate derivatives. It's not too complex, but I kind of got hung up on it when I was learning as well, and I hope that makes sense. So those are the two different ways to notate derivatives, to say, hey guys, this is a derivative. Yeah. So it's over there, f prime x, or you can have this. Another funny observation is that if you solve this out into a Cartesian equation, or where it's just y equals thing, then it'll have it'll be the derivative of y divided by the derivative of x. And so then it'll actually be a fraction, but at the same time it's not. It's just the notation is weird like that. Actually, sorry, just real quick. You can skip the video now if you want. T, we're going to solve for x. So x over 8 equals t squared. So root of x over 8 equals t. And then we're just going to substitute that back into the y. So 3 root of x over 8 equals y. And now if we take the derivative of this, I'm going to use some stuff that I haven't taught you yet, but it'll make sense later. It'll be 3 over 2 over 2 times 1/8. Okay, so that's going to be 3 over 16 root x. Hold on, I think I messed up somewhere. 3 over 16. Okay, so I'm missing a gap here. Honestly, it kind of shows where I'm missing something. But you can see how the derivative of y is 3, and it's going to be 3 on top, as it corresponds with this. And you divide by dx, it's going to be something like 16t, but, oh yeah, and then t is equal to x over 8. I forgot. Root of x over 8. There we go. You just take t back and you substitute it in. And yeah. 3 over, derivative of 3 divided by 16, and then t is root of x over 8. 3 over 16, root of x over 8. That's exactly how it works. Just a quick observation, but don't get confused. D of y over d of x is not the same as a fraction. We're saying the derivative of y with independent variable being x. And that's what it is. Okay, hope that makes sense.